Dear friends, this is my tutorial 13. So in this video I'm going to tell you how to execute AIMD calculation in VASP and analysis with VASPKIT and VMD. So this is the system, FENC system. I'm going to tell you how to prepare input file and do the AIMD simulation using VASP. So this is FENC system. So why we want to do AIMD? So this is to check the thermal stability of the catalyst. So basically people will do 300K and 500K and 900K. You can do this three kind of temperature, so you can see your stability of your catalyst. So then we can plot that AIMD results produced by VASP using a VMD and VASPKIT. So we can also plot the figures for bond length waste time and RMSD waste time, and people also will plot total energy waste time and also the temperature waste time. So this kind of the plot the people will plot. So I will tell you how to plot these things later. Now I will show you the in-car file for AIMD simulation. Now I will show you the in-car file for AIMD simulation. So this is the AIMD input file for my AIMD simulation. So first I will show you the parameter for in-car file. So this is the in-car file for AIMD simulation. So this is the system name, so you can give your system name. So this is based on the computer core NPR. Based on your computer you can give this value. So this is the general parameters. So here we need to I start 1 and I charge also 1, precision normal, so it is enough, and grid also false. So LTL auto you can give. So important things, isometry you can put 0. This I mentioned what are the things. Okay, these are the important things, so you need to check once. So IDI pole also 3. This also you can go n right equal to 0. So these are the general parameters. So then we can see the motion, cell and geometry optimization, relaxation. So here you can see eyebrow you need to mention 0 only. So here I mentioned 0 for MD, 2 for that conjugate gradient optimization. So these are different kind of things. So you can give eyebrow 0 for molecular dynamics, ISIF 2. Here only we going to relax the atoms only, so not in the cell. Then you can give NSW 500. This is the how many steps you want to perform. Okay, so if you see here maximum cycle of optimization, so if you see here, so I mentioned 5,000 steps equal to 10 picosecond. So that means with potium 2, if you are if you give potium 1, so 1 into 5 into 5, so the 5 picosecond will do the calculation. So basically I will use potium 2 5,000 cycle, and that means 10 picoseconds. Okay, so basically if you want you can also give 6,000 here, because in initial 1,000 steps you may see some more fluctuation. So to overcome this you can maximum put the 6,000 steps. So then the initial 1,000 steps you can ignore and use other 5,000 steps for your publications. Okay, you can also do like that. And I already told you potium equal to 2. I always mention 2 only. Some people also will use 1. So if you use 1, it will get the 5 picoseconds like that. So then you can mass equal to 0. So 0 is NVT ensembable. This you have to mention. So an MD algo is this no C over thermostat. We have to use this one only. So here you see the time initial. You can initial temperature 0 Kelvin. So time beginning is 5,000 step, and the time not time beginning, temperature beginning 500 Kelvin, and the time temperature end also 500 Kelvin. So if you want to give other temperature, you can want to give 900, you can give here also you can give 900. That means your calculation will for 900 degree Kelvin temperature. So these are the important. You can use also NB log 1 for dynamics calculation. And also here see the important SEF parameters. So NCAT I used always 400. So then I spin 2 so all go fast. So if you use very fast, it may not converge, so you can use fast algo is, I think, is best for this kind of calculation. NLEM equal 100. This is, you can also give maybe 1000, maybe I think 100 is enough, that minimum, that SF cycle. So and EDIF I used here 110 to the power minus 5 0.5, so we can use this is enough. Then ISMR equal to 0 and sigma equal to 0.2, this is enough. Then functional we will always use GGA and PE. So this is the in-car file for molecular dynamic simulation. So I will share this file to you. You can use it, do molecular dynamics calculation and perform. So then we will see the K-point file. So this is the K-point file. I always use K-point file for molecular dynamics is gamma point 111, because if you use that higher level of K-point, so it will take a lot of computational time and computational resource also. That's why I use always 111 for molecular dynamic simulation. I think it won't affect that system, I think so. So you can also try to use this kind of small K-points. Then I will show you the postcard file. So this is the postcard file. So this is the carbon 66 atom, nitrogen 4 and Fe1 atom. This is the postcard. I will show you the structure using Vista. So this is the structure. So this is actually optimized, so energy minimized structure. So actually before you do the molecular dynamics, you need to minimize your structure. So then take that file for the molecular dynamic simulation. Then port car file. So here I use 3 kind of port cars. So I will show you. So here carbon first, second is nitrogen, third one is Fe atom. So this is the postcard file for the corresponding postcard file. Then you can use your submission script to do the calculations. Okay. So that's all the input file for AIMD simulations. So actually I already submitted this calculation and completed. This is the graphene FEN for AIMD simulation. So next video I will make you how to get the result from that, the AIMD output files. Okay, so I will show you how to get the different kind of data from there. Okay. Thank you for watching. If you like my content, please like, subscribe and comment and share, and also please click bell icon for my future updates. Thank you. Thank you for watching. Thank you for your valuable time. Dear friend, this is my tutorial 13.1. So this is the extension of previous video. So last video I told you how to make in-car file for AIMD simulation and submit the calculation. So in this video I'm going to tell you how to extract the result from the AIMD output files. So let's see. So this is the folder I have completed the AIMD simulation for the graphene supported FE system. So first we need to convert this xdatcar file to PDF file to use VMD software. So first we will see this. We will do this. So now you type VASPKIT. Then you can see here 72 molecular dynamics kit. So type 72. Then you can see different kind of things. First we will convert our see AIMD trajectories of selected atom with the PDF format. So we can now convert into the PDF format. So you can type 737, okay, 737, just enter. You will get this second option. So you can select one, okay, select one, then you can type all, then you will get data for all. That's all. So I think how many frames you want to skip, I will always put 0. Here also I will put 1. That's all. Our AIMD trajectory PDF file created. So we can use this file to plot bond length versus time. So this is a AIMD trajectory PDF file. So next one is we need that RMSD. So for that, again click VASPKIT, go to 72, and you can see here mean square displacement and mean square displacement using FFT. I recommend that they mention, so I will use this one only for my calculation. So you can also type 722. Here also you type 1. So you can type your number of which atom you want. So I will type if you see our output file means so we want only nitrogen and iron atom, okay, we don't want any other atom for RMSD. So just we type our nitrogen space and Fe. So these two atoms for enough, that will take care of this. So just enter. So here also I will put 0, don't want to skip. So if you are using 6000 steps, so that time you can skip 1000 steps like that. Here also put type 1. That's all. Return MSD data and diffusion coefficient. This is the very important file. We can plot our RMSD VAS time. So that's all. You can use this VASPKIT to extract this result. So I think we have got the two results. So AIMD trajectory file and so MSD dat file. So you can copy this. So this is the two file we want to plot the AIMD result. So first I will show you trajectory things. So for that we need VMD. So you can download yourself VMD from the website and install it. So this is the VMD. So you want to open this file into VMD. So go to file, new molecule, not new molecule, otherwise you can also drag. So after dragging, that will run all the 5000 steps. So you can go to here, display, orthographic, graphics, reference station, go to bond or CPK, then close it. I think 5000 steps over. So if you want, you can also see. So from this here you can start from 0 to, you can see the, I think we have did the 500 Kelvin temperature. Some initial 1000 steps, you can see the more fluctuation. So after that maybe the bond length are somewhat stabilized. Yeah, just you can see everything. Yeah, it's over. So we need to get the bond length of this 4 connection with the iron atom. So we will start with here. Okay, so for that so this is the thing. So now you can press 2. So that time you will get that plus arrow. If you type if you press 2, you will get this kind of plus arrow. So now you can select your bonds, whatever you bond want, you can select it. So we want only this 4 nitrogen with connected with Fe. So you click here, this is one bond. So click here, click here, click here, click here, click here, click here. Okay, we have selected 4 bonds. Okay, so just to go here, graphics, maybe labels, I think more things is there. I think we did something wrong. Just you select everything. Delete, we will do 1 second. So you type, already we typed that 2. So select this one, 1, 2, 3, 4. So this is the thing. So sorry, here items that we need to mention bonds. Okay, if you see here, we have selected 4 connection with Fen atom. So this is the things. If you want to see graph also, you can see graph. So you select this one, you can see preview graph. So likewise, so if you want, you can close it. So the second atom, if you want, you can also see graph. So likewise, this is the 4n connected with the Fe atom. So we will save one by one. So be sure first your atom is there, you need to convert into, change into bond, then you will see the bonds. So you go to graph, so save your files. So you can make the numbers, maybe that will be very easy to understand. So first one is, we have clicked this one. Okay, so you see the numbers of this atom is 67, 71. Okay, this is 67, 71. Okay, so first what we selected, '67. Okay, type 67 N2 Fe, save. Okay, second you select, so second atom number, second item number is 69. Okay, you can save 69 N to FE. Okay, third one is 70. You can click save. 70 N FE. And last one is 68. Then save. Yeah. So like that, if you want any other bonds, you can mention in that VASPKIT get that bond distance of the systems. So that's all. I think our files are saved. So now we will plot our result, the bond length versus time. Okay, so just open one file. This is earlier I did, so just to close it, that no need. So you can close these files, no need this graph we need. So first 67 you can drag, you can click OK. So finish it, it will come your result. So then add additional columns. This is a 67 NFE. This is 68 NFE. 69 NFE. 70 NFE. Okay, so first one we copied, then we need to copy the second one. So just OK, finish. So this is 68, just copy paste, make it one Excel sheet. Then 69, and also copy 69. Okay, and delete this one. Then 70, finish it. So that's all our 4 bond distance results we have uploaded into the Excel. So just we can plot, select this 4 column, go to plot and plot line. So we will get these results. So I will tell you how to arrange. So you can 3 you have mentioned, we can also put one, this also -3. Oh, -3 is too large, you can do 0. I think that's enough. 0 or 1. So adjust like this. And also here also you can adjust 0 to 5000. So I already told you the initial 1000 steps, maybe you will see the more fluctuation. So if you want, you can do it into 6,000 time steps. So 6,000 steps, then you can ignore these 1000 steps. You can make it another 10,000 steps, add to your this 4,000 in order to make 5,000. So okay, just we can make it this plot. So already I made it one plot. So we can copy. So distance. This is the femtoseconds. We converted into picoseconds. So just to remove this, delete that one. Just you can make copy paste. Paste, and you can put Control Z, it will come automatically the same place. So you can make grids, then it looks good. So you can make it somewhat bold, the outside layer. So you can also make independent underline. You can go, can give your color whatever you want. Just I will leave like this. So you can make it 2. So everything you can click, you can make it. Then it will look somewhat good. So make your based on your choice of colors. Just I'm leaving like that. So if you want, you can also change. So violet. So like that, you can make it your own color. So you can arrange it. So you can make N1 to FE, N2 to FE, N3 to FE, N4 to FE. So you can go here, frame, I think you can give none. Okay, if you want to bold, just you select one by one, click it bold. Yeah, this is the things. So you can also arrange this. Increment 0.5. So click bold and 22. Okay, that's all. You can put your name of the system. Just so this is important, temperature and thing. Just copy it. So our system is 500 Kelvin, I did. So this is so FeN4C, this is the 3N1, N2, N3 for Fe bond. Okay, you can save it now. So this is the distance west period time plot. So you can export. So always use JPG. So name so you can save it into the corresponding folder. Just copy the pathway and keep here. So make it somewhere 600. Yeah. I think our figure is saved. This results shows that our catalyst is thermally stable under 500 Kelvin. Okay. So that's all. Next we will see the RMSD VASP time plot. So this is also a very important plot. So actually this is the file, MSD file. So you can see here different kind of parameters. So we want to plot only this time, picosecond. This is square MSD, so square root of MSD. So we are going to plot this one and this one only, not this any other thing. I think these are no need. Okay, so just I will close this. So I open one, this already I made one plot. So that's okay. Just drag our data. So this is our data. So this is the last one, only important one. So just to select this, no need select this one. You can select just to plot. Go to plot line. So you'll get like this. So so why are coming 10,000 means we have mentioned that two in the porting 2 times steps, so that's why you're showing 10,000. So we can make it into 10 picoseconds this. So we can adjust this one 0 to 10,000. So you can also adjust this. So -1, you can also do -2, I think +2. Yeah, this is our system. You can also make it here. This is our RMSD, square root of RMSD VASP time thing. So you can make also here also grids. So you can also make color, some different color if you want. So already made one figure for this one. Just I will copy that things from here. Just copy this data. So 500. So you can type FEN4 at. This is the RMS device time slot you can use for this your future research. So you can make like this plot and do it yourself. Yeah. So now we can save this, export. So we already saved, so we can go directly there. You can change into JPG. You can type RMSD this time. So mainly I will do these two analysis only, though this is I think very important. So you can also do it yourself. And you will see our RMS device time plot. Yeah, just crop. So this is our RMS device plot. It shows that this is highly stable catalyst under this kind of temperature. So I will share these files for your reference, so you can download it and use it yourself and do your own AIMD calculations. So if you like my content, please like and subscribe and comment and share, and also please click the bell icon for my future update. Thank you for watching. Thank you for your time. Happy computing.